All right, so airflow and bypass dynamics. But just remember, we are here for you. So if there's anything you need, reach out to us, 800-611-8312. We are proudly made here in the US. Our products are supported, and if you call us, you can reach us after hours, 8 a.m. to 9 p.m. Eastern Time, 7 days a week. We are here for you to keep a strong partnership with our contractors and to provide them with all the information they need to succeed when installing zoning. But today we're going to talk about static pressure, so airflow and bypass and how those two tie in together. The questions that come up the most are, do we need a bypass and what size? And oftentimes it turns out that no bypass is necessary. So I want to talk about how we can determine that. But increased static can be a good thing. It really can be our friend. When we increase our static, we get better destratification. We can decrease duct BTU loss because the air is moving through that duct faster. It spends less time in contact with the duct surface area itself, so it sheds fewer BTUs. So more BTUs make it into the zones rather than staying in the ductwork itself. We can satisfy those zones more quickly because we're targeting the area that needs that BTU gain or that cooling the most. And when we target that area, we satisfy it faster and we make it more comfortable because we're destratifying. So when we look at satisfying zones too quickly, maybe the equipment's oversized. Oftentimes we run into an issue of pockets of hot air, pockets of cold air, things like that. But when we use zoning appropriately and we increase that static, we do satisfy the zones more quickly, but we're forcing that air into the zone at a greater rate, and that helps to reduce those hot and cold spots. It causes more mixing, more churning of the air, and it helps to reduce those hot and cold pockets within that area. Very similar to what you would have with a small duct high velocity systems. They move air at a high velocity, they forcefully churn the air within that area, and it helps to destratify. It removes those hot and cold pockets because it churns the air at a more effective rate than what you have with a standard velocity system. And then if we have an area that's hard to reach, area that's out of the way, bonus room over the garage is a perfect example, or the lofted area upstairs where the ductwork is almost sufficient, but it's marginal, and they do have some comfort issues. Now, if the ductwork's way too small, we need to get more up there. But to that, more BTUs to hard to reach areas. So if it's an out of the way place, it's that bonus room over the garage. Maybe they decided to add some runs and finish off their basement, but it robbed velocity from upstairs. Places like that are perfect for zoning because we can deliver more BTUs in a targeted way to satisfy those loads. But some of the cons that we can have, if the ductwork's not sealed, we increase our duct leakage. So we're going to push more air out the drive seams, out the clip seams. We're going to push more air out of the connection point for takeoffs that aren't sealed up, or the gussets on our elbows, things like that. So it can increase duct leakage if we're not sealed up. Now, while some duct leakage is accessible, if we have significant duct leakage, then we're really wasting the benefits that we would have from that increased static, because we're now pushing air into unoccupied zones, or we're potentially pushing air into unconditioned zones if the ductwork runs through an unconditioned area outside the building thermal envelope. It can cause excessive airflow noise. So the higher we push that static, the more feet per minute we have coming through our register, the greater likelihood is that we may run into a whistle, and that's going to cause nuisance issues for our customer. And then it can be damaging on the equipment if we take it too far. So most furnaces, not most, all furnaces, when you open up that manual, are going to have a blower performance data chart, and that's going to give you a maximum static pressure. For the vast majority of furnaces, that maximum total external static is going to be 0.8. Recommended total external static is 0.5. Most furnaces should be really designed, if everything's open and calling, to be running between 0.4 and 0.5. And then once we apply zoning, we want to push that up as high as we can, but we really don't want to exceed the maximum rating for that blower. which is typically around 0.8. And if we're exceeding that, we can damage our equipment and shorten its life expectancy quite a bit. But BTU delivery, under normal conditions, we're moving optimum airflow, we're moving the BTUs the system's designed for, but airflow likes to take the path of least resistance. So while we might be doing that, we may not be delivering those BTUs optimally to the zones that are calling. So when we install zoning, it allows us to channel that. It allows us to cut off those paths of least resistance and control the air, sending it where it needs to be. It's like putting guardrails up that people can't bypass or that air can't bypass. It allows us to control it and to effectively deliver it to the places that we want it to be. Some things we can do for measuring our duct performance. If we take our return air temperature at the furnace, we take our supply air temperature. So the supply air minus the return temperature gives us our temperature rise. And then we can take an outlet temperature, an average of, let's say 3 to 5 supply registers. So our plenum temp minus our supply average. So that's the air that we have exiting our furnace, our supply air temperature, minus our supply average. And then we divide that by our temperature rise. We can get an idea of duct BTU loss. And I strongly recommend classes by NCI. They have some really good classes on duct performance, on what they call air improvement. What can you do as an air upgrade for your customer? Maybe they're not ready for an entire overhaul of the system, but how can you identify the best air upgrade for their application? And NCI has some really good classes in regard to that. Being that we're a manufacturer, I really kind of give you a mile-high overview of everything, but if you really want to dig into the nitty-gritty, strongly recommend some of the classes by NCI for their ductwork. But how can we put that into application? So let's say I measure my return air, 68, my supply air, 130. I get my register average, 97, 101, 108, 86, 93. So I average that out to 97 degrees. So now I've got 130 minus 97 divided by 62. So that gives me 0.53. So my ductwork, my measured performance for my ductwork is 53%. So I'm delivering about 53% of the BTUs from my equipment into my zone itself, the rest, or into my area of control itself. So my ductwork is 53% efficient. Or at least my ductwork is losing 53, not 53% efficient. My ductwork is losing 53% of its capacity. Now, according to the EPA, the average duct loss should be between 25 and 40%, and that's average. But if I look at this system the way it is, I can see that I've got 53% loss. So I'm losing 53% of my BTUs not actually being delivered where it needs to be at. So I can see that my ductwork is performing worse than even the average duct system that the EPA has registered or the EPA has recorded. So if I'm looking for a target between 24 and 40% loss, and obviously the lower my loss is, the more I can get that down, the more effective my system is, the better I'm going to be, the more efficient my system's going to be for my customer as far as BTU delivery goes. So here I'm losing 53% of my ductwork, and there's definitely room for improvement to that. But for that, we can then do some quick calculations. And one of the big improvements we can make is duct sealing. Now, if the ductwork is sealed itself, maybe we've taken things to an extreme to where we're just not moving the air that we need, or maybe our ductwork is grossly oversized and we're not delivering it effectively to where it needs to be at. So really we need to take a look and see how our ductwork is performing in that application. So in the last class, I gave the formula for velocity times square inches divided by 144. Now, if you've got a means of measuring velocity, or you've got a means of measuring your CFM, I like that little CPS Bluetooth dongle that I can connect up to my phone or tablet, and then it gives me my velocity. And then I can use my duct chart. I can use a quick reference chart. I can use that formula that I gave you. Then I can convert that into CFM to see what I'm actually delivering. And once we convert that to CFM, we can also convert it to BTUs. But taking a look at that formula again, we got velocity times square inches times 144. If I have a 6-inch round duct, that's 28.27 square inches. So if my branch design velocity is 450 feet per minute, that gives me 88 CFM through that 6-inch round duct. If I have my slide chart, I'll see that my slide chart is within a couple of CFM of that. If I use a duct reference chart, and that one I just kind of put together based on that formula, but there are some groups out there like NCI that have a quick reference chart for you that includes the static pressure that gives you the best performance, and then it tabulates out what your quick reference should be as far as CFM goes. So if I know what my design is, I can measure my actual performance. So my design for that 6-inch duct is going to be 88 CFM. Now, if I use my meters and I measure my actual performance, I might see that it's not running at that 88 CFM. It might be running at less than that. Maybe instead of 450 feet per minute, my meter tells me I'm running at 300 feet per minute. So now I know that that register is underperforming, and I need to take a look at balancing out my ductwork or installing zoning, because maybe my ductwork's oversized, or maybe I'm pushing far in excess of that. And now my static pressure is high enough to the point where I can damage my equipment when I measure that out. So it gives us an indication of where our airflow is going, and knowing that, we can convert it to BTUs. So under perfect conditions, laboratory testing kind of conditions, I can take that 88 CFM, my 6-inch runs, 88 CFM each, I can convert that into BTU delivery. So my BTUs are 1.08 times my CFM, and that happens first, and then I multiply that by my temperature difference. So if I got my room air of 68 degrees, I have my register outlet of 102 degrees. That tells me that I'm delivering 6,463 BTUs into that area. So I have two 6-inch runs, each one's running at 450 feet, or each one's got 450 feet per minute coming out of them. That's 88 CFM each, so I've got a total of 176 CFM. 1.08 times the 176 multiplied by my temperature difference, so 68, 102, that's a 34-degree difference, gives me a BTU delivery of 6,463. So if my ductwork's designed perfect, everything is operating optimal conditions, this is what I'm actually delivering into that area. But we know that that's really not what's happening. This is practical knowledge, but once we actually start measuring, we'll see that our ductwork doesn't line up to this at all. We'll see runs that are overperforming. We see runs that are underperforming, and air balancing is an important thing. But we need to look at ways that we can improve our duct performance. One of those is sealing our ductwork. Another might be resizing it. Maybe we need to increase the size of our duct going into a specific area so that we can increase our BTU delivery. If we've got ductwork running outside of the building's thermal envelope, so it's running through an attic or an unconditioned crawl space, that needs insulated. Another thing we can do, because it does improve our velocity, so we can push that up to a maximum. We can, if we're running at a minimum velocity, then this is where the manual D charts come into importance, is because they give us a range of velocities that we're looking for. We can design our ductwork for those velocities. And when we're looking at installing zoning, we want to design for the low to medium end of the velocity without zoning, and then zoning will push us closer towards the high end of our maximum velocities to give us the the best performance on that system. So sealing ductwork, resizing ductwork, insulating, installing zoning. And being that we're a zoning company, I'm really here to focus on the zoning side of things. But our zoning increases our velocity, and some velocity increase is a good thing, as long as we're not pushing it so high that we can damage our equipment. But as we increase that velocity, the airflow through our equipment can slow down, and that's going to collect more BTUs. So we're going to have hotter air. We're going to have in the summer months, we'll have colder, drier air. In the winter months, we'll have hotter air. It'll be more forceful, which is going to help destratify. But we really want to stay away from micro zoning, because if we take those zones down too much, we push our static too far, we create nuisance issues with noise for our customers, and we potentially damage our equipment. So we have to be careful when we are applying zoning. We don't want to push it so far that we're going to damage the equipment. We also don't want to push it so far that we create a nuisance issue for our customers. So in the next slide, we're going to talk about how the BTUs actually affect that delivery rate. So if we remember our design velocity at 450 feet per minute, once we zone that down though, we can take that formula and find our CFM. So now if I have if my design velocity was 450 feet per minute, now I've zoned it down and I've got a recorded velocity of 600 feet per minute. So that 600 feet per minute gives me 130 CFM each. So now I've got 260 CFM of capacity being fed into that zone. Now, if my temperature stays the same, then that shows me 9,547 BTUs. So I have a 48% increase in my BTU delivery to that room itself. And that's a significant improvement. I went from about 6,500 BTUs being delivered without zoning. Now I'm delivering about 9,550 BTUs. So it's a 48% increase in BTU delivery into that room, into that zone. So that's going to be hotter air. That's going to be more comfortable. Because the airflow does slow down though, that 102 degrees wouldn't be completely accurate. So I might actually see that pushed up to 110 degrees. So zoning has a couple of improvements that it makes. It improves the velocity, but because I'm also collecting more BTUs from my heat exchanger, I've got more heat being transferred into the air being delivered to that. I might see my register outlet temperature increase. So instead of 102 degrees, maybe I'm going to have 110 degrees. And at that 600 feet per minute, that's actually going to give me almost 12,000 BTUs of delivery, 11,700, 11,800 we'll say. And that's an 82% increase over the BTU delivery that I had without zoning at all. But then we can take that and we can use that formula that I gave you earlier to talk about how that affects our ductwork. So if you remember before, there was a 53% BTU loss through our ductwork. But now with the zoning system, we've got a slightly higher supply air temperature. I've taken my register average of the zone itself, and calculating that out, I see that now I'm only got a 36% BTU loss, which puts me within that EPA range of 24 to 40%. Now it's still on the high side, so there's more improvement that can be made. But these are simple calculations that we can do with our customers. So if we have a way of measuring that velocity, we can get our customer involved. Maybe they hold our tablet and they read the feet per minute for us while we move our meter over top of the register, and we see that change as it's recorded. We have them with us while we collect our temperatures. And then we can calculate that out to show them how their ductwork is performing. We can calculate that out to show them what kind of BTU loss they have through their ductwork. And this is a way that we can get them involved and show them that there is room for improvement. And while this is something that we don't have a lot of information for at the start of when we start doing this. The more often we do it, the more data we collect, and we can use that as evidence of improvement for future customers. We can show them that, hey, I had a job very similar to yours in the past. We made these improvements for them, and this is the performance increase that they had from it. And these are some very simple things to do. And in this case, this one's just temperature. I don't even require that little velocity meter. So I'm taking my temperature rise. Are you able to see the screens, Brad?
Yes.
Okay. It doesn't seem to be working on my end too well, but as long as you're able to see them, we're good to go.
Yeah, I've got them.
But this is just a very simple thing. I'm taking my temperature rise. That takes what, 10 minutes? If I'm letting my equipment run for a period of time to stabilize, I get my temperature rise. I'm taking my return, my supply, and then I kind of walk through the house and I get the average of 3 to 5 registers. Once I have those 3 numbers, I can easily calculate out a BTU loss for their ductwork, and I can say there's room for improvement. So in this case, my measurement before zoning showed that I had a 53% BTU loss. Now, once I zoned it down and I took measurements in an individual zone, I see that that individual zone only has a loss of 36%. So there's an 11% improvement to the performance of my ductwork to that individual zone. So as a whole, 53% loss. As a smaller portion of that, 36% loss. So that's an improvement that I can measure and I can show my customer. And this really only takes about 15 minutes. And that gets your customer involved. That's something that a lot of companies aren't going to do with their customer, but this gets them involved, and that helps to set you apart. It shows that you're doing something above and beyond. And while it's a simple thing to do, it sets you apart as being above and beyond because you're showing them and you're getting them involved in the process, and they're being more responsive to you for that. So our air pressure is the blood pressure of our system, and that really gives us the heartbeat of what it is we're working with. And we want to be able to show the customer tangible improvements, and the only way we do that is by measuring performance before and then measuring performance after, and then we can show them the difference that our improvements have made to them. And if you really want an in-depth course with regard to determining what improvement's going to make the most performance impact for your customer, strongly recommend the classes from NCI. They're good classes, and they'll help you identify the problem spots, whether it's the return that needs the most improvement, the supply that needs the most improvement. If you need to really focus on both of them together or one side or the other, they have some great classes for that. Have I lost you yet? Do you have any questions?
No, well, I was just looking at one of the slides before, and I may have missed it. So in that equation, it's the supply air minus the average divided by, and was that 67 was a factor that stays the same? Because the return, I don't see where the return, or is that supposed to be 68 with the return error?
Oh, that's supposed to be 68. I carried over the wrong number.
Okay, no problem. I just wanted to make sure that I had it noted in my notepad there that essentially that's the return error, because I saw the difference there. I wanted to make sure 7 wasn't a constant.
No, it's not a constant. It's your return temperature. It's my typo, but yeah, you're taking 5 to 7 temperature changes, and you're calculating that into a quick BTU loss. And these aren't really my calculations. I got them from Engineering Toolbox, and if I'm not mistaken, this one actually came out of a trade magazine where they were talking to contractors about how to identify the need for improving ductwork. And it seemed like such a simple thing to me that it really ties in well with zoning, because when we look at how zoning increases the velocity, that velocity changes our duct BTU loss because it spends less time in contact with the ductwork. Now, if we've got significant enough duct leakage, then we need to correct that, and that'll drive our number down further. But optimum velocity, duct sealing, air balancing, that's going to give us the best BTU delivery and the best comfort for our customers. The trick really comes into identifying which difference is going to have the most significant impact for your customer. And NCI can really help you out with that regard. Their classes are really good. I sat through one of them, and it gave me a lot of information that I already had, and for the most part, it's stuff that I kind of look over. But when they started tying that into identifying where the greatest area of improvement was, that helped me in some regard, because I already knew the vast majority of the information they were going over. This was one of their more basic classes. I wanted to see how it was presented, and they took the vast majority of the information I already had, things I already did, but they put it in a new light to narrowing down the focus of what improvement is going to make the best performance impact for my customers. And that was something that I found helpful. So while already having the information in my head, they helped to narrow it down more, so I wasn't looking at the broad picture. I was then focusing on the greatest place for improvement, and that was something I found beneficial. So strongly recommend their classes.
All right.
Because we're a manufacturer. I give you a mile high overview, but their sole focus is on performance, and being that that's where their sole focus is, yes, their classes are expensive, but they are worth it. And they're a training organization dedicated to performance improvements. And if you're not really involved with carbon monoxide testing, they have some fantastic classes for that too. I believe those are on hold because of COVID-19, because for that you really need to be in person for those classes, using the meters, testing it, seeing exactly how things respond to it. And that's a lot harder to translate to an internet class. But they have some really good classes with regard to safety testing, and then a huge focus on performance testing. They'll spend 2 days going over something that I'll cover in 2 hours. That to me, I'm not certain how they do it, but somehow they make it engaging enough that they really break it down to its base elements, and I can't recommend their classes enough. Because what I cover in 2 hours, I can't figure out how to stretch it out. They cover it, and they make it feel like it's a full class, and they really break it down to its base elements. And that's something as a manufacturer we don't do. We're just a mile high overview, and they break it down to the brass tacks. But we got a couple of different things that we use for measuring performance. The one that we're probably most likely going to be using is going to be our static source tube. That's the one that comes in almost all of our manometer kits. But there's a couple of different tubes that we can have. You're not going to see the simple pitot tube a whole lot anymore. You're not going to see the pitot static tube a whole lot anymore, because we have digital meters that can read our velocity for us. Those ones aren't quite as necessary for us in the field. But those were means of reading pressures so that we could calculate out our velocity with the manometer or a magnehelic. But being that we have meters, hot wire anemometers, we got the impeller anemometers, like that little Bluetooth dongle that I like. Those give us our feet per minute in real time, so it makes it a lot faster and easier for us, fewer calculations. But our static source tube is going to be our most common tube that we're using for actually measuring to see if our equipment's running outside of its specifications. So if we're exceeding our maximum static pressure, that's the tube that we're going to be using to test our total external static. We're going to use it to test our external static. So our external static is just our supply air duct by itself. And that's not looking at our equipment, that's just looking at our supply air duct. So typically without zoning, our main trunk line is going to be somewhere between a 0.07 to 0.12, or at least it should be based on design. Now in reality, we're going to see that it's significantly higher than that when we start testing equipment, because we're finding that furnaces are oversized for the ductwork or the ductwork's undersized for the furnace. Now our equipment needs to be designed to handle the actual load that the house needs. And then once we have our equipment design, we need to make sure our ductwork is designed to match that equipment. If the ductwork is pre-existing, this is where it's important to try and recognize what improvements we can make to have the best performance impact on that equipment to give them better operation. But without zoning, your main ductwork normal design should be somewhere between 0.07 and 0.12. If you look at your duct slide chart, residentially it says 0.1. Our branch ducts, on the other hand, our branch ducts should be designed between 0.4 and 0.08. So our branch ducts, the rounds coming off of our main trunk line, are designed at a slightly lower velocity than what we're going to design our main trunk line for. Our main trunk line gives us the pressure to push out, but our branch ducts reduce that pressure to overcome objectionable airflow noise. And then with zoning, if our smallest zone is calling by itself, we're typically going to see that somewhere between a 0.17 and a 0.30. And the closer we get to that 0.30, the more likely we are to have objectionable airflow noise for our customer. Nominally, you're probably going to end up somewhere around a 0.17 to a 0.23. Because once you start exceeding that 0.25 and you're pushing it up close to that 0.3, and this is our external static, so this isn't our static running through our equipment. But when we start pushing it up too high, we do create objectionable airflow noise. We have that velocity noise coming from the registers, potential for a whistle, depending upon what kind of registers we use, and that can be a nuisance for our customers. But your test should be done about 12 inches away from your transitions, 12 inches away from your return plenum, because transitions are a turbulent spot. We want to give that air a chance to kind of smooth itself out so we can get a more accurate reading. And then be mindful of airflow noise. So that's our external static. That's our supply duct static. That's our return static. If we're measuring that, our return design is actually a lower velocity than what we're going to design our supply duct at. And Manual D has a nice chart. Your return, according to the chart that I have in Manual D, and I don't think we discuss it in this PowerPoint. That's going to be in a different class where we go more in depth into duct design. But the chart has your supply duct designed a maximum of 900 feet per minute, I believe it was. So design for your supply duct is between 600 and 900 feet per minute. Design for your return duct is between 500 and 700 feet per minute. And then your branch ducts are 300 to 700 feet per minute. So that helps us when we look at our slide chart. So rather than looking at that friction of 0.1, we're now designing based on the velocity that we're trying to achieve. And the 0.1 is pretty close. And if we look at that 0.1 and we follow the line out, it gives us our CFM. We actually see that the other side of that static gives us our feet per minute. And when we follow that line out, we see that our feet per minute does end up within that parameter that we have for the Manual D chart based on the friction that we're looking to achieve. So if we're looking for a 0.1, we actually see that on a 6-inch duct that comes out to the 500 feet per minute, I believe. So 0.1 at 100 CFM on a 6-inch pipe, I want to say came out to about 500 feet per minute when we follow that through on our duct slide chart, which is within that range that we're given according to Manual D. So it's a nice simple chart to follow. We can use that with our ductulator to really calculate things out fast and easily and see what we're designed for. And a lot of times what we run into residentially and commercially, it's not so much a problem of supply terminations, it's a problem of the duct that feeds those branches being inadequate to actually supply those branches, more often than not. Our total external static, though, is what our equipment's rated at. So on the vast majority of residential equipment and most light commercial, we look at that, it says maximum design total external static is 0.5. But then once we look at our blower performance data chart, we can see that maximum total external static is actually in most cases probably closer to 0.8. Some manufacturers allow you to go up to a full inch, but in all reality, those ECM blowers shouldn't be exceeding 0.8 and they shouldn't be staying above a 0.7 for an extended period of time. Just talking with some tech guys from an equipment manufacturer, and one of them did mention that the maximum velocity for the, or not maximum velocity, maximum static pressure for the ECM blower on that particular brand of equipment, if you stay above a 0.7 for an extended period of time, it will damage the motor. And zoning doesn't keep you at those static pressures for an extended period of time, especially RZL zoning, because during an off cycle, our dampers fully open. So when your motor goes to start and stop, it's starting against a low static and then it's ramping up to the higher static, and then it's able to stop by ramping back down to the lower static. And in talking with Chris Mahalik from Regal Malloy, where they manufacture a lot of these motors, the majority of the motors that we're going to run into on the market, his remarks were because of the way the zoning works in that it allows the motor to start against a low static and ramp up to the high static, but then ramp back down for the off cycle. It allows it to start and stop against an appropriate amount of back pressure, and that doesn't damage the motor. And it's because it's able to ramp up safely and ramp back down safely, we're not going to damage the motor by exceeding that static pressure rating because of the way it works. So with our system, your motor is able to start against open dampers, ramp up to the higher pressure, and then as your equipment goes to cycle off, the RZL dampers revert back to open, and that allows that motor to ramp back down to a static pressure that's acceptable for it before it shuts off. So we can take that and we can push it higher, and we can give our customers better performance. But our total external static is what we're measuring to see if we're operating properly according to the blower performance data chart. And while our rating plate says 0.5, the blower performance data chart is typically going to give us a maximum of 0.8, some manufacturers up to a full inch. So we talked about these charts when we were looking at two-stage furnaces in the last class. But airflow without zoning. So a 5-ton blower, no zoning. I've got my Y1 inputs. I got my Y2 inputs. With my Y2, everything open, I'm running a 0.49. So I'm meeting the design static pressure for my equipment, 0.5. I'm at a 0.49. I'm golden. And I'm using 467 watts on that variable speed blower. And you can see that my feet per minute is between 300 and looks to be about 405 feet per minute. So I'm within design, slightly underperforming since I'm looking for 300 to 700 feet per minute here, but it just shows that I have room to balance out my runs and direct the airflow a little bit more effectively. And then when I look at my Y1 input, I'm running a total external static of 0.19. I'm using 101 blower watts, so I'm using a lot less electricity, but my air really has no force behind it. So I'm not delivering a whole lot of airflow. Great for circulation if I'm trying to clean the air in my home, but not necessarily for BTU delivery. It's great for air conditioning because that lower blower speed is going to allow for a much longer run cycle. In these northeastern states, I'm in Northeast Ohio, it allows us to dehumidify the air more effectively, and that's going to improve the comfort a lot greater than having large BTU delivery. But once I start to zone it down, and I take it down to, in this case, I took it down to the most extreme, 15% of my ductwork to my equipment capacity. So I've got 3 6-inch runs open on a 5-ton blower. And if I figure my 6-inch runs each being 100 CFM each, that gives me 15% for the 3 6-inch runs. Now my static is way too high for my Y2. I'm running at a 0.92. And for this particular furnace, my maximum allowed is a full inch. So while I'm within that maximum, I really don't even have to be there. And I can see my blower watts, I'm using 679 watts. That's a lot more energy than I was using prior. But if I use the RZL Heat Pump Pro and I utilize a zone weighting, I can lock my furnace into a Y1 capacity. And now I can see my total external static at 0.485 is reasonable. It's within maximum for that. And my blower wattage is less than half of what it was before, 197 watts versus 467. So I'm using less than half of the electricity. And looking at my feet per minute coming from my registers themselves, 498, 538, 736, I see that I have a little bit of room for air balancing to bring that third register in, because that'll increase my velocity from my other registers. But I look at my average CFM delivery. So I got 173 CFM being delivered into that zone with the Y1 blower using half the amount of energy that my blower was using prior to deliver almost twice the airflow. So I have a lot more airflow delivery. That airflow is going to carry more BTUs. It's going to carry more comfort. It's going to increase the performance, and it's going to make my customer a lot more comfortable, a lot happier with the operation of their equipment. But I have to be mindful that I'm not pushing things so far that I'm going to damage my equipment. So I don't recommend the Y2 blower here. I probably wouldn't want to see your static pressure getting up that high. I prefer to see it a little bit lower, closer to that 0.7, 0.8 range, not exceeding the maximum that you're going to find for the majority of equipment out there. But you're still going to maximize performance by increasing that velocity, increasing that BTU delivery. So the RZL Heat Pump Pro, best panel for the application. It gives you your zone weighting. So like we saw in the previous slide, I had my Y1, my Y2. The zone weighting feature with my Heat Pump Pro allows me to set a percentage, and that percentage disables my W2, Y2 outputs until I reach enough zones calling. And if I have a mix of big zones and small zones, I can set this up so the big zones can use it, the small zones can't, and I can really tailor the equipment operation to the zoning system and the zone breakdown that I have for my customer. Field customizable wizards, so you can set the settings. A lot of them are adjustable, and that allows you to really match the comfort to what your customer is expecting. There's leaving air protection, so if your equipment's getting too hot, it's going to stage it back or stage it off. If it gets too cold, it stages it back, stages it off. Single stage, multi-stage, dual fuel, conventional, all electric. All of that can be done with just a basic thermostat RWGYC, or in the case of zone 1 thermostat, RW1, Y1, G in common. Heat pump thermostats are not necessary. 2-stage thermostats are not necessary. The panel is capable of controlling all your staging. It's capable of controlling your reversing valve. It's capable of controlling dual fuel changeover. And you can use a basic thermostat to provide a call for heat, W, a call for cooling, Y and G, or a call for fan, G by itself. Panel will control all those outputs for you. So if you notice, there's two sets of Y contacts. There's air handler Y1, Y2. There's condenser Y1, Y2. The air handler outputs are controlled based on zone size, so zone weight. If you don't meet your zone weight, W2, Y2 are disabled to your furnace air handler. If you do meet your zone weight percentage, and that's customizable, W2, Y2 are allowed. Now you get a Y2 output right away, but your W2 output is subject to a 9-minute delay. Now your condenser outputs, Y1, Y2 condenser, those are based on your leaving air temperature. So if you can maintain your cool stage threshold or your heat stage threshold, if you can maintain that with the first stage compressor, the panel's not going to stage up your condensing unit. If you need that second stage condenser, so maybe it's getting real cold outside and you have a heat pump system and you want to run the compressor itself more aggressively, but it's a small zone. That's going to allow you to run a Y2 condenser output for that smaller zone while still running a Y1 blower output. So your airflow is more closely matched to the zone, but now you have increased heat capacity. So you're going to get hotter air from the heat pump delivered into that zone without needing to run your electric backup heat. And it's a performance improvement. It increases the comfort for our customers. So some examples of zone weighting. I got a large zone at zone 1, 50%. I've got a medium sized zone at zone 2, 40%. I've got two small zones for zones 3 and 4. So I set those at 20%. And then I leave my air handler stage threshold at the factory default 50. So 50 is equal to 50, W2Y2 is allowed. 40 is less than 50, W2Y2 is disabled. 40 and 20 is greater than 50, so W2Y2 is allowed. But now I got my small zones. 20 and 20 is 40, 40 is less than 50, W2Y2 is disabled. But now if I got 20, 20, and then my medium-sized zone calls, that's going to be greater than 50, so my W2Y2 is allowed. So with this, rather than having a minimum calling zone, I have a true customization because I have a zone that's allowed. I have a zone that requires a little more capacity, and I have two zones that require a lot more capacity. And now I have it set up to where those zones utilize W2 and Y2 based on what they are able to for the conditions that I provide. So I can set all that up. Now with this, my minimum calling zone may be zone 1 by itself. My minimum calling zone may be zone 2 with any other zone, or it may be that I require 3 zones. If zones 3 and 4 are being served, they can't use it until a third zone calls. So it's a true customization that allows me to match W2, Y2 for the actual size of my zones and to set any combination to disable it until I have 1 zone, 2 zone, or 3 zone calling, all with the exact same panel. So static pressure, great tool. We need to measure it, we can calculate it out, and then we can make our adjustments. And when we do that, we can maintain maximum performance for our customer. So static pressure is our friend. Using it appropriately is going to give us the best control for our customers. So it looks like we're just over halfway through. It's a fair time for a break if you want to take one, Brad. Otherwise, we can keep going.
I'm good to just keep going.
Okay. All right, we'll keep moving through it then.
All right.
So the pros of static pressure. Well, the pros of bypass control. And when we use bypass control, the only real pro to it is for reducing airflow noise. If we use it as a means of static pressure control for ductwork that's already too small, we're going to run into other problems later on. So if our ductwork is designed appropriately, but we have a small zone, then bypass can be an effective means to reduce that airflow noise and to ensure that we're not causing a nuisance issue for our customers. But if our ductwork is already too small for the equipment, bypass isn't going to be the solution because when we have to oversize the bypass to compensate for poor ductwork, we take a lot of the load off the equipment. So we're short cycling it through our equipment. It's going to overheat it during the winter months. It's going to overcool it during the summer months. That's going to cause short cycling. It's going to cause us to run on our limits. It's going to, if we don't have a TXV on our evaporator coil, that could cause liquid flood back to our compressor. All bad things. The short cycling, not healthy for the equipment, not good for the electric bills. The overheating, freezing of coils, all of it's just bad stuff if bypass is misapplied. So if the ductwork's too small, it needs to be improved before we really apply bypass or before we apply zoning. If the ductwork is good to go without zoning, then we can apply zoning. And if we have a zone that runs on the small side, we can selectively use bypass or some other means to reduce the pressure enough in that zone so we don't create objectionable airflow noise or excessive static. Small zone optimizers will be wild runs. That's a run that has no damper in it at all. It just blows free. A good application for those is going to be a mud room or an entryway, or if they've got a two-story glass wall, those runs against that glass wall, we might actually put a smaller damper in there instead of the full-size damper, and that allows a metered amount of air to just constantly wash in that area, and that can help to reduce the airflow noise. So wild runs are one option. If we have a zone that's too small, but it's not necessarily a problem of under conditioning, it's a problem of over conditioning. So in the summer months, that area constantly gets too cold with the air conditioner running. In the winter months, that area gets too hot with the heat running. The alone zone allows you to damper off that area by itself based on a thermostat control and a duct sensor detecting if there's heat or if there's air conditioning running. So if the thermostat calls for heat, the duct sensor says it sees 90 degrees within the supply duct. It allows that damper to open, satisfies that heating call, thermostat turns off, damper closes, stops the over conditioning. Cooling call, we're looking for 60 degrees or less. So the thermostat calls for cooling, leaving air temperature is 60 degrees or less. The damper opens, thermostat satisfies, the damper closes, we stop the over conditioning. And then the last option that we really look at is going to be the bypass. As long as it's designed appropriately, you're fine. But if it's way oversized, it does cause problems for the equipment. So we need to be mindful about how we're sizing the bypass duct. So when we're looking at a bypass duct, if you call us here at RZL Support and you want help sizing a bypass, we need to know your equipment size, your tonnage. We need to know if you're using trunk dampers or branch dampers. And we need to know the CFM on your smallest zones. If you call us for help with zone weighting, I want to know the CFM on every one of your zones. But if you're calling us for help with bypass sizing, I just need to know the CFM on your smallest zone by itself. And that's nominal CFM. So if you got 4 6-inch runs going to it, figure it 400 CFM. That's really what we're looking for. What is it designed to handle without zoning? That's your smallest zone CFM. And when I'm looking to design my bypass, in the testing that we've done, a bypass moves moves the air through itself because it's got two forces to contend with. It's got the return air pulling, it's got the supply air pushing, and those two forces move air through that bypass duct at a much greater rate. So it's moving air through there at about 2,000 feet per minute. In our testing, it's 1,800 to 2,200 feet per minute. So right down the middle, 2,000 feet per minute. And this is bypass design only. This is not standard duct design. This is bypass duct only. And we want to size it to reduce the objectionable airflow noise because too big of a bypass is going to be bad for the equipment. And oftentimes it's worse than if you had no bypass at all. So bypass used to be designed based at 1,000 feet per minute, 700 feet per minute, normal manual D calculations, and bypasses were huge. or they were just oversized. So let's say I had a 5-ton system, 2000 CFM. I had 4 6-inch runs, 500 feet per minute, 400 CFM. So I need a 1600 CFM of bypass to maintain that 0.5. And to get that, I would have to do at 700 feet per minute, a 21-inch round duct. At 1,000 feet per minute, that would require a 17-inch duct. So if I had a small zone, I'm trying to maintain that 2000 CFM through there, which we're really not, but this is how it would have been designed back in the day. And this caused short cycling, this caused poor performance, this caused problems with the equipment. But knowing that a bypass duct can move air at 2,000 feet per minute, if I have a 21-inch pipe, that actually calculates out to 4,810 CFM at 2,000 feet per minute. If I have a 17-inch pipe, that calculates out to 3,152 CFM for a 17-inch pipe. So both of those at 2,000 feet per minute, because we have that push and that pull force, are enough to dump the entire capacity of that blower between my supply and my return. And when I do that, I've got no air making it into the house at all. So sizing our bypass duct appropriately is huge. And learning how to do that is going to increase the performance for our customer. So based on the testing that we've done here in-house, and we did a lot of this testing back in the day with NCI, the National Comfort Institute, which is why I really like to push contractors towards their classes to learn more about ductwork, testing, air performance upgrades, things like that. Great classes. We've worked very closely with them in the past, and they helped us learn how to appropriately size the bypass. So what we came away with from working with them is that when we're designing our bypass, we want to maintain maximum comfort. And if we pay attention to our blower profiles, we actually see that a comfort profile moves air at about 350 CFM per ton. We also know that we're not going to run into a risk of freezing an evaporator coil until we start dropping down below 240 CFM per ton. So for comfort with zoning, to maintain maximum velocity, we design our bypass based on 300 CFM per ton. Now the ductwork itself, absent zoning, has to be designed at that 400 CFM per ton. But when we're looking at our bypass duct by itself, we design that at 300 CFM per ton to maintain maximum velocity, maximum performance. So now a 5-ton system for maximum comfort, as far as the bypass is concerned, is 1,500 CFM. My 4 6-inch runs, though, I'm looking to move about twice the amount of air through there, between 800 and 1,000 feet per minute. So I can get up to 800 CFM through those 6-inch runs if I push them far enough. So that gives me a bypass requirement of now 700 CFM, and at 2,000 feet per minute, I can fit that through an 8-inch pipe. So this is where we are going to have to be a little bit careful, because this is going to take care of about 85 to 90% of the people out there. But you do have those few customers that really are sensitive to air or to noise. And we have to gauge our customer, because if we have that customer who's sensitive to noise, we want to adjust this a little bit. So rather than 200% airflow through those 6-inch runs, we're actually going to figure that at 150% airflow. So instead of 800 CFM, it'd be 600 CFM, which would give me a bypass requirement of 900 CFM, and that would actually be a 10-inch pipe rather than an 8-inch. So we have to be careful to make sure we gauge our customer appropriately and determine what's going to best suit their needs, because an 8-inch pipe, probably 8 out of 10 times is going to be appropriate, but you'll have the 1 or 2 customers there that you're going to probably want to take that up just a little bit so that you can dump a little more air if necessary. But that's where installing 2-stage equipment really plays into this, and using the Heat Pump Pro with its zone weighting, because now instead of trying to force that 5 tons of capacity through the 4/6-inch runs and then a bypass to compensate for it, I can use my zone weighting, and then my bypass is going to be designed based on my first stage airflow. And in the charts that we saw prior, I can fit 5 tons of air through 4 6-inch runs. I could fit it through 3 6-inch runs. I probably wouldn't fit it through 3 6-inch runs unless I had an 8-inch bypass on there under normal conditions. But I can fit that first stage capacity through 4 6-inch runs and not require a bypass in most cases. So two-stage equipment plays a really important role in maximizing comfort, performance, and reducing the need for a bypass. And the Heat Pump Pro is the best zoning control on the market because of the way it uses its own weighting. It's a true customization rather than just a minimum calling zone. So if I'm sizing my bypass now and I have a two-stage furnace, I'm going to size it based on low stage capacity. And what I would find in this application is that bypass isn't necessary. So start with the end result in mind. What am I looking to achieve for my customer? Smallest zone, I want to maintain maximum static without creating objectionable airflow noise. I want to maximize my BTU transfer, and I want to minimize my bypass. So it's really only about overcoming objectionable airflow noise, because your customer's perception of noise 9 times out of 10 is going to tell you that there's a problem with your static pressure before your meters are even connected. Now, it's not to say we don't connect our meters, because if anybody's like me, their hearing doesn't work anywhere close to what the customer's hearing works at. So I need numbers to work with, and those numbers allow me to set it for what I've typically found to be the maximum tolerable pressure without creating objectionable airflow noise. And then I let my customer gauge it. If they say, yeah, it's a little bit loud, then I can go make small adjustments to it, and I can start cracking it back, and I can start dialing it in. And then I might take it to the middle range. So let's say my customer perception of airflow noise typically becomes a problem if I start to exceed 0.8, which is going to be my maximum for my blower performance data chart. I might start there at 0.8, let my customer listen to it. They say, yeah, it could be a little bit better. I'll take it back to 0.75. And then I let them listen to it. I've got a number to work with, and then I let them listen to it. I say, we've made a little bit of adjustment. I brought that down a little bit. Can you take a second, listen to it? Yeah, a little bit more. Then I'll take it down to 0.7. And I found that the vast majority of my customers, when I brought it back to 0.7, were happy with it. For the ones that were happy at a 0.7, they were happy with it. But I had that number to work with. And because my hearing didn't work the same as my customers, I knew the number that I wanted, and I worked with that and allowed them to make that judgment call of, is it good, or do I need to take it a little further? So numbers for me, I could see it because I couldn't hear it, and mostly because I've done a lot of duct installation. My ears ring incessantly, and my hearing just doesn't work like the homeowners. Unless it comes to my kids. My wife, she's a saint. I don't know how she puts up with the noise of all my kids. So where should our bypass duct be? It's a great question. Bad place for bypass duct. Why do you think this might be a bad place for a bypass duct?
I am turning my phone sideways to see that just a little bit better. That
It's going to be the most common installation, but it's a bad place for it.
because it's got too many turns, or just has turns, which essentially are going to
Well, not quite.
reduce its capability.
So your plenum is a mixing pot, but that's also going to be the most intense for your BTUs. and your return drop is so close to the furnace that there's no real tempering of those BTUs. So you're taking the hottest part of your furnace and you're dumping it directly back into the furnace without any means of tempering it to bring it to a more reasonable temperature. So I'm
Okay.
superheating my return air and I'm going to run my limits, or I'm supercooling my return air and I'm going to tank my coil temperature, and that's going to have huge performance and efficiency impact on the equipment itself. So you're taking the point of the greatest BTUs and dumping it so close to the furnace that there's no chance for it to temper itself with the air coming back from the home, and we're going to really hamper the efficiency of our equipment by doing that. Another application, and there are some zoning companies out there that recommend this. We don't, and the reason being is that on your supply side, the end of your duct is the point of your supply duct that creates your back pressure. That is the highest point of pressure in your supply duct that allows you to actually pressurize your supply and force your air through your branch runs, which is also why in any duct design class, they will strongly recommend you never come off your end cap. You always make sure you're at least 12 inches back from your end cap. And the reason being is because if you come off your end cap, you lose your back pressure in the system. So while this may very well be great for dumping excessive pressure, you're dumping that pressure into the point of lowest draw on your return air. So your return air is going to pull its greatest closer to the drop. It's going to pull its least furthest from the drop. Your supply air, you're losing your back pressure and you're forcing your greatest amount of pressure back into your lowest amount of draw. And now that's going to turn your return airs into supply airs. So if that area of the home isn't calling, you've pressurized your return airs, you've turned them into supplies, and now you're forcing air through your return duct out into that zone that's not calling. So when you're installing a bypass duct, it should ideally be about 8 to 10 feet away from your equipment. And we recommend that you don't come off your reducers, because reducers are meant to increase the pressure to have a more equal pressure as you move down your return ducts. So try to be about 12 inches away from reducers, 12 inches away from fittings, 12 inches away from your elbows, because those are pockets of turbulent air. And when we come off of those areas, we kind of mess up the airflow in the rest of the system. So your bypass duct, whenever possible, should be installed on your main trunk line itself before your first reducer, about 12 inches before your first reducer, and hopefully that's about 8 feet away from your plenum. And then on your return side, it should be about 8 feet away from your drop. On your return side, this is going to give you a point that may be subject to the maximum draw, depending upon how your returns are laid out. This may be a more medium draw, but we're giving that BTUs a chance to diffuse into the home before we dump it back through our bypass. And now when we dump it into our return, we're giving it a much greater length of duct to mingle with the air from the home coming back into the furnace. So it tempers it, and we have a less extreme temperature overheating our return air. So we're giving it a chance to deliver that capacity to the home before we start to dump it through the bypass, and then we're giving it a chance to temper itself before it's drawn back through the furnace directly. So that's why it's really best to have that bypass duct about 8 feet away from the equipment whenever possible, but before your first reducing adapter, preferably.
Now, I do have one question about that. If all of your, is this supposed to happen before zone dampers?
No, I'm not so concerned with that.
Okay, because that's the only question I have
I'm
there.
not so concerned that it happens before your return dampers. I'm more concerned that it happens before your first reducer. So if you've got 8, 12 feet of let's say 24 by 10 duct, and then you're shrinking it down to an 18 by 10 or something like that, I'd like to
Yeah.
see it about 12 inches before that reducer shrinks it down. Um,
Okay.
that way you're coming off of the majority of the airflow, but at the same time, you've given it the opportunity to go to the home before it bypasses if those runs between there and the furnace are calling. So you shed some BTUs through those other runs, and instead of dumping the full BTU load back into the return for that pipe. So try to be about 12 inches away from reducers and fittings. Try to be about 8 feet away from the equipment whenever possible. And if you've only got 4 feet of pipe or 4 feet of trunk line before you shrink it down, then put it on the next section of ductwork. It's more important that it be about 8 to 10 feet away from your furnace than it is that it come off that first portion of duct whenever possible. Now, it's not always probable to do this when someone uses trunk dampers instead of branch dampers. So if that's the case, you may not have the option of coming off of your trunk line with that bypass duct and you have to come off your plenum. But if you have to do that, then run the pipe down the return air so it's not coming directly into the drop. So take the pipe that you're using as a bypass, get it away from that drop, and don't just dump it directly from plenum into return air drop.
Okay.
Yes, it just causes a lot of performance issues when you do that, and more often than not, somebody calls me up and says that the furnace is constantly running on limit. It's because of where the bypass is installed, or it's because the bypass is oversized more often than not. So
Okay.
proper installation helps to maintain performance. So when you're adjusting that bypass, start with your smallest zone calling by itself. If you have a 2-stage furnace and you use the Heat Pump Pro, have it running in low fire, that or low stage. That way you're setting it up based on that calling. And then make small adjustments to it. Read with your meter, see how your static pressure is looking, see if it's going to be objectionable for your customer. And if your customer is satisfied with it, you're good to go. You'll probably find more often than not that bypass isn't required. So it's a good thing to measure your static pressure, get your customer's perception before installing the bypass duct. And then if your pressures say you need it, and if your customer's perception of airflow noise says you need it, you price it into the job, you have it available, go ahead and install it. But if your customer's satisfied with it, you don't have to put the bypass in. If your numbers say you're good, you don't have to put the bypass in. And now you can just return that to your distributor or stock it for the next job. And that's profit on the job. But get your homeowner's input, because if your ears are anything like mine, they don't work like the homeowners. And then check the airflow delivery. I needed the numbers, and that's why I checked my static pressure with my meters. And then I let my customer give me some input, and then based on their input, I would leave it alone, or I would turn it back a little bit more for them. And then we've made it real simple for you. There's an RZL bypass chart that's available. If you go to our website, www.rzlzoning.com, click on or hover over the products tab, click on dampers, and then about 2/3 of the way down is a big blue button that says download bypass sizing chart. You'll see that there's 2 sides to it. We prefer the branch dampers because the branch dampers give you a lot more trunk line for that air to really kind of straighten itself out in, and it's less turbulent. And when it's less turbulent, it requires less bypass, and that helps to make for a better performing system overall. But there is a side to it that allows you for trunk dampers, and it gives you some quick sizing for trunk dampers as well. And if you notice, the bypass goes up, it gets bigger. And the reason it does that is because it's more turbulent. That turbulence requires a larger bypass to overcome. So if you can, branch dampers are the best way to go for maximum performance. If you can't, you have to use trunk dampers. that's fine, but be aware your bypass calculation does change slightly because of that. So there's a quick size chart available for you. Take care of anything residentially from 2-ton to 5-ton. If you need help with sizing a bypass for commercial applications, something greater than 5 tons, let us know. Just call us up, smallest zone CFM, blower tonnage, and we'll be able to help you calculate that out. A couple of options available for you. The barometric bypass damper doesn't work very well with ECM or variable speed motors. It's fast reacting, so you really need that only for PSC blowers. The response time of those is too quick for an ECM or a variable speed motor, so it opens and it closes, it opens and it closes. And when it does that, those ECM motors will start ramping up and down. They start hunting, trying to find the RPMs that they need to be at, and that causes nuisance problems for the customer as well. So we take those calls every now and then. The homeowner calls us up and they describe the situation for us, and it turns out somebody installed a barometric bypass on a variable speed blower, and that blower is ramping up and down because that weighted arm barometric responds too quickly. So for that, we worked with the Regal Malloy Gentech Motors, and we developed our ModuPass. It's a modulating bypass that works based on static pressures. It responds slower, which is good because it allows that motor to find its RPMs, and the damper itself responds to what the motor needs. So under normal conditions, we got full pressure from our pump going into a damper, and it's a spring-loaded damper. That damper wants to, without any pressure, push itself open, but that pressure wants to keep it closed. So if it's getting full pressure, the damper stays closed, but then as our supply static increases, the transducer that comes in the kit for the ModuPass controls a bleed off of pressure able to go to that damper. And in there's a small restrictor there. I suppose I need to change the coloring for that lettering, 0.012 restrictor, but that restrictor goes between the transducer T and the panel, and it causes a slow enough buildup in pressure that now that transducer that you see there is able to control the amount of pressure going to that damper, and it controls it somewhere between 0 and 20 inches of water column. And that allows that spring to now modulate that damper based on my supply static. So as my static increases, the damper opens more. As my static decreases, the damper closes more, and it responds slow enough that my variable speed ECM blowers can find their RPMs and they can run appropriately without causing issues of ramping up and down or hunting. So if you have any questions though, reach out to us, 800-611-8312. We are available 8 a.m. to 9 p.m. Eastern time. Are there any questions? Because I'll breeze through the warranty procedure since you've already sat through that last week. But do you have any questions with anything we've discussed?
No, not in particular. Like I said, of being able to talk offline about that particular job we spoke of would be interesting to get some of that information. I apologize for the laughter earlier at all of the information I was just picturing this particular job. So it's going to be very, very interesting and a great example to be able to learn from this particular job itself in regards to bypass and everything else.
Yeah, no, a lot of it comes to start with everything open, measure your static pressure and see where you're at, because with everything open, if your static's really high already, then you know you have to improve the ductwork before zoning can really be fixed.
Yeah.
So if your static's really high, ductwork improvement needs to be made. And I think you rightly identified one of the big issues, and that's your return air. Because with a 5-ton drive, your return air is too small. And we'll talk about that a little bit more later. So identifying the ductwork improvements that need to be made, hugely important, because zoning, Zoning can take good ductwork and make it fantastic. It can take bad ductwork and make it worse. So it can take marginal ductwork and make it good. It can take good ductwork and make it fantastic. It can take bad ductwork and make it worse. Is essentially what I like, what I typically say. Because if your ductwork is really undersized to begin with, then zoning is going to make it worse, and you're going to damage your equipment. You're going to have unhappy, uncomfortable customers. If your ductwork is marginal, meaning it's right on that edge, you might. So So a perfect example of this is a lofted area. The lofted area being, we'll say 600 square feet. They've got 4, 5, 6 inch runs going up there, but the rest of the house is really kind of taking the vast majority of the capacity for that equipment. Those runs may be sufficient under normal conditions or under design conditions to handle that upstairs, but because all my pressure bleed off is on the main floor of the home, I'm not getting the capacity through those runs. So zoning can take that and it can make it so I get the capacity I need through those runs to condition that area. Another really good spot for those is when I worked new construction, bonus rooms over garages were being a huge thing. And we would make ductwork amenities for it. We would typically run a duct large enough to handle that area, but because the builder did not want to finish that bonus room, they didn't pay to have the furnace size to handle that bonus room. And since the bonus room wasn't being done, oversizing the furnace would have caused comfort issues with the main part of the home. So the furnace was sized to handle the home as it was without the bonus room, but the ductwork was run there to provide means for it later. And when the customer ultimately 5, 6 years down the road decides to finish that room, the ductwork is there, but the furnace capacity isn't. So once we zone that down, the main floor of the home doesn't need zoning, or the main floor of the home doesn't need conditioning because it's really kind of insulated from heat loss through the ceiling since there's a floor above it. It's got a basement below it, so we're not really sucking heat out of there. It's really just got the few walls, and there's very little heat loss, heat gain on the main floor of the house. So now I can take the capacity that would have been there and deliver it to that bonus room, and now I can satisfy the whole home without having to replace the equipment. I just finish the ductwork in the bonus room, put the zoning in, and I deliver the capacity where it needs to be at with the zoning system. So I block it off where it's not necessary, deliver it where it's needed, and now the ductwork that was marginal because they hadn't, we'd made plans for it, but they hadn't decided to do it. The ductwork that was marginal now works and meets all the needs of my customer. So takes marginal ductwork, makes it good. Good ductwork makes it fantastic. Bad ductwork and makes it worse. So it's all about design. It's all about what we're looking at and making those improvements. So RZL has a lifetime parts warranty as long as it's registered within 90 days of installation. Your customer can register, you can register as a contractor, but it is lifetime parts. And we're really simple to work with. All you have to do, technician on site calls us 800-611-8312, and we will help them take care of the warranty. January 1st, 2013 to present is when we had our lifetime warranty started. So anything prior to that, panels were 5-year, dampers were 10 years. So some dampers will still be covered out until 2022 based on the parts and labor warranty. But as far as lifetime parts warranty goes, there's no longer any labor, but it is lifetime parts to the original homeowner if registered within 90 days of installation. Registration's fairly straightforward. You go to our website, click on products, warranty information, and click on the link for lifetime warranty registration, fill it out. We need the panel serial number, and then you're good to go. We'll send you a confirmation email once we receive it. If technicians run into a problem, they suspect there's warranty, they need to call us while they're on the job site. We've had a lot of contractors lately where the technician went out, diagnosed it, didn't call tech support, and we've had to send them back. And when they go back and they finally call us on site, it turns out that the problem wasn't with the RSL system. The problem was with something outside of it, and they misdiagnosed it. So the reason that technicians need to call us when they're on site is, one, it prevents the office from having to send you back on a call that you've already diagnosed. Two, it helps you to make sure your diagnosis is right the first time. When you call RSL Tech Support, we're going to walk you through some diagnostic questions. If it is the RSL system, we have no problem taking care of warranty. We're not here to deny the warranty, but we are here to make sure that the diagnosis is correct, because RSL has a very, very reliable product, and our failure rate extremely low. We have a low enough failure rate that more often than not, it turns out to be a misdiagnosis. And that's why our warranty process is the way it is. Technicians need to call us on site so we can walk through some diagnostic questions with them, verify the failure. If it's RSL, great, we'll take care of you. That's what we're here for. If it's not, we help to point your technician in the right direction so that they aren't misdiagnosing it. I had a contractor just the other day. Their technician was out, diagnosed it, they went back for the repair. Turns out it didn't fix it. He didn't diagnose it right. So he diagnosed it again. And this time he's going for the most expensive component in the RSL system, but he still hasn't called us. So we're not going to warranty it out, especially not control boards, unless the technician calls us from the job site so we can walk through some troubleshooting questions with them. And if they call us, we're really easy to reach. 800-611-8312. We're available 7 days a week, 8 a.m. to 9 p.m. Eastern time. So there's really no reason technicians can't get a hold of us. But there are some technicians who absolutely refuse. In those applications, warranty may very well be denied. If they go through their distributor, most of the distributors will tell you you have to call RSL Tech Support. For the ones that don't, the warranty may still be denied, or it may be subject to a 20% processing fee. So very important, technicians call us while on the job site, 800-611-8312. Panel serial numbers, we need those to verify registration. So if it's an older system, don't just go promising them warranty. We need to look it up, verify it was registered, verify its age. If the panel was unregistered, while the policy is 1 year warranty, RSL does offer grace out to 5 years. Tech support department, we believe in matching the minimum warranty that you would get with your HVAC system if it went unregistered. So while most furnace manufacturers offer you 10 years with registration, 5 years without, here in tech support, we believe in honoring a warranty out to 5 years to at least match what you had with your HVAC equipment. But for that, technicians have to call us while on site, and we need that panel serial number so we can look it up to verify registration. If it was registered lifetime, great, we just need a verified diagnosis. If it's not registered, we need to verify diagnosis, and then if it's less than 5 years, we will help you with the warranty. But if you need anything, contractor resources available to you. If you want to schedule trainings other than what we've got pre-scheduled here for webinar Wednesdays and OCILB Fridays, you can schedule a custom webinar at your convenience and we can discuss other topics. Those are freely available to contractors and we can do those at your convenience. Monday through Friday, typically 9 a.m. to 4 p.m. depending upon the class. Some of them take up to 3 hours. If that's the case, we like to get those scheduled to start no later than 1 p.m. That way we can be finished up with it by 4 and able to take the phone calls for the technicians that wait until the very last minute of the day to call. So webinars, quick, convenient, and easy. Schedule those at your convenience. We got lots of webinars available for you. Just let us know how we can help. Our Comfort College temporarily on hold. So that's why we're doing our OCILB Fridays. If you need any marketing literature, let our team know. marketing@rslzoning.com. More than happy to get you out some literature to have some leave behinds for your customers, some information pamphlets with regards to the panel, or a zoning product guide that discusses all the RSL products, gives you a picture of the product, and it gives you a brief description of what that product's for. And that helps to keep in memory the different dampers that we offer, because we have quite a few dampers that we offer to meet different applications out there for you. So rzlzoning.com, really good resource for you. If you haven't registered, click on contractor sign up. If you have registered, thank you. There's a lot of information available for you there. All of our installation manuals, some helpful troubleshooting videos for technicians. So it doesn't have to be a company-wide account. Strongly encourage technicians to register independently, and then they can have access to all that right from their smartphone or tablet or computer while they're on the job site. But any help you need, 8 a.m. to 9 p.m. Eastern Time, 800-611-8312. All right, well, I appreciate your time, and it looks like I actually finished on time.
Perfect.
So, all right, I'll look for that email from you. My email is joel@rzlzoning.com, or you can send it to tech support@rzlzoning.com, listed there on the screen. Jason and I will both get it, and then I'll review them and give you a call back.
You said it was Joel
Yep.
at RZL Tech Support
rzlzoning.com.
or rzlzoning.com.
Yeah. So all of our emails end with @rzlzoning.com, just like you see there on the screen. If you want to get a hold of me directly, it's my name, joel@rzlzoning.com. If you want to get tech support in general, because if I'm not seeing my email, but you want to make sure you get a direct response faster, tech support@rzlzoning.com emails myself, Jason, and Ken. So all three of us get those emails, and you're going to get a response faster. But if you need to get a hold of me directly, we've been discussing something, joel@rzlzoning.com.
All right, excellent.
All
Joel,
right.
thank you very much.
And I appreciate your time.
And yours.